Hi all, welcome to new class. Today's class is about the second order system in control systems. So before that, what is order? Order of a system. The order of a system is governed by the order of the differential equation of the system. So order of a system means it is the order of the differential equation governing the system. And the order can be determined from the transfer function. So, let the transfer function be k into p of s divided by q of s, where k is the constant and p of s the numerator polynomial and q of s the denominator polynomial. And the input and output relationship of a control system is expressed by the differential equations. So, let the transfer function be p of s divided by q of s, and the order of the system is given by the maximum power of s in the denominator polynomial. So, order of the system is given by the maximum power of s in the denominator polynomial, that is q of s. If q of s is equal to a0 s raised to n plus a1 s raised to n minus 1 plus etc. plus an minus 1 s plus an, then n. This n is the order of the system. So, if n is equal to 0, it is 0 order system. Then n is equal to 1, then first order system. Then if n is equal to 2, it is second order system. And this order can be specified for both open loop system and closed loop system. And also the value of n gives the number of poles in the transfer function. So the order is given by the number of poles of the transfer function. So order means the maximum power of s in the denominator polynomial. Also it is equal to the number of poles in the transfer function. Let us study the response of first order system. So, the closed loop transfer function of the first order system is given by c of s divided by r of s equal to 1 divided by 1 plus ts. So, the highest power of s in the denominator polynomial is 1. So, this is the first order system. Then, for the unit step signal, let us study the response of first order system with input as unit step signal. So, for the unit step signal, r of t is equal to 1, that is r of s will be equal to 1 by s. So, we can write c of s, that is the response in, this is the response in s domain. So, c of s equal to r of s into 1 divided by 1 plus ts, that is 1 by s into 1 plus ts. And to get the time response, we have to find the inverse Laplace transform, that is we have to find c of t. So for that we have to find the inverse Laplace transform of this one, that is C of s equal to 1 by s into 1 plus Ts. So for that we go through the partial fraction. So to go through the partial fraction expansion, for that we are arranging this one, that is 1 by s into, we take this t outside, so here we can write 1 by t divided by s into, this will become s plus 1 by t. Now we can do the partial fraction expansion. So this c of s we can write 1 by s, that is 1 by t divided by s into s plus 1 by t, and this is equal to a divided by s plus b divided by s plus 1 by t. So this is by partial fraction expansion. Now we have to find the values of a and b and substitute here. So to find the value of a by partial fraction expansion, this denominator into this one at s equal to 0, that is partial fraction expansion. So to find a, s into LHS, that is 1 by t divided by s into s plus 1 by t at s equal to 0. So put the value of s equal to 0. Before that we can cancel these two. So at s equal to 0, the value of a is equal to 1. Now to find the value of b, in this way we can find the value of b, that is s plus 1 by t, s plus 1 by t into LHS, that is 1 by t divided by s into s plus 1 by t at s equal to, so here what is the value of s? To get the value of s, equate this denominator equal to 0 and find the value of s. So while equating the denominator of this b factor equal to 0, that is s plus 1 by t is equal to 0, then we get a value of s as s equal to minus 1 by t. So here we have to substitute at s equal to minus 1 by t. So here these two are cancelled and put the value of s as equal to minus 1 by t. So this minus 1 by t and this 1 by t are cancelled and we get the value of b as minus 1. So b is equal to minus 1. Now substitute the values of this a and b in this equation. So let this equation be equation 1. So we get equation 1 implies c of s equal to 1 divided by s. The value of a is 1. So 1 divided by s. Then plus b by. So minus 1 divided by s plus 1 by 1 divided by t. So this is c of s. Now we have to find the value of c of t. So c of t is Laplace inverse of c of s. And we get Laplace inverse of 1 divided by s minus 1 divided by s plus 1 by t. So Laplace inverse of 1 by s is 1 and Laplace inverse of 1 divided by s plus 1 by t is, so this is e raised to minus t divided by t. So here 1 divided by s plus a, that is the Laplace inverse of 1 divided by s plus a is e raised to minus a t. So here A is 1 by t. So we get minus 1 by t into this t is here. So minus t by t. So this is C of t. And after putting the values of t from 0, that is put the values of t as 0, then t, then 2t, 3t, then etc. up to infinity, then we get the response. So the response of the first order system be like, with the unit step input signal, it will be like this. So this is t and this is the response is 0, C of t, then 0, then t, 2t, 3t, etc. So this is the response of the first order system with unit step input. Now for the unit impulse signal, C of s equal to R of s into 1 by 1 plus st. So this is the first order system, and putting the value of R of s equal to 1, that is for impulse signal R of s equal to 1. So we get C of s equal to 1 divided by 1 plus st, and by taking the Laplace inverse, C of t is equal to this, we can write 1 by t divided by s plus 1 by t. So after taking the inverse Laplace transform, we get C of t as 1 by t e raised to minus t by t. And the response of the first order system with the impulse input is like this. This is C of t and this is t from 0, t, 2t, etc. Now for the unit ramp signal. So for unit ramp signal, C of s is equal to R of s into 1 divided by 1 plus st, and for unit ramp signal R of s equal to 1 divided by s square. So after substituting this 1 by s square into 1 plus st, and here also we can write 1 divided by s square into here 1 by t, then s plus 1 by t, and by partial fraction. So here while taking partial fraction, this will become a divided by s, then plus b divided by s square. So here there is a term s square. So in partial fraction expansion, we have to write first the first order, then the second order, a square, b divided by s square, then plus c divided by s plus 1 by t. So after solving, we get C of t is equal to minus t plus t, then plus t into e raised to minus t by t, and the response will be like this. So this is the response of the first order system with the unit ramp input 0, then t, 2t, etc. Next is the second order system. The standard closed loop transfer function of second order system is C of s divided by R of s equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square, where omega n is the undamped natural frequency in radian per second and zeta is the damping ratio. The damping ratio is defined as the ratio of actual damping to the critical damping. And this zeta can be represented either like this or like this. So anyway you can write this theta. So this is the damping ratio. And the response. So response is C of t. So C of t of the second order system depends on the value of this damping ratio. And depending on the damping ratio, the system can be classified into 4 classes. So depending on the value of the damping ratio, the system can be classified into 4. First one is, if the theta is equal to 0, it is called undamped system. And if theta is equal to 1, then it is called critically damped system. And if theta is greater than 1, it is over damped system. And if the theta is between 0 and 1, it is called under damped system. So here the damping ratio can be this zeta, or this is the tau. So here this tau can be represented here. So basically it is called zeta. And there is a slight difference between this tau. Tau means this is tau, and zeta. Zeta is like this. So you can represent either in this way, or this is zeta. So in your convenient way, represent zeta. So here this is zeta. The characteristic equation of the second order system is s square plus 2 theta omega ns plus omega n square equal to 0. So after solving this quadratic equation, we get the roots as s1 and s2 is equal to minus theta omega n plus or minus omega n into root of zeta square minus 1. So when this zeta is equal to 0, we get s1 and s2 is equal to plus or minus j into omega n. And when zeta equal to 1, we get the roots as minus omega n. So here when zeta is equal to 0, the roots are purely imaginary and the system is undamped. That is, zeta is equal to 0 means it is undamped system. And when zeta is equal to 1, the roots are real and equal. So the roots are real and equal, and the system is critically damped. And when zeta is greater than 1, we get the roots as minus zeta omega n plus or minus omega n into root of zeta square minus 1. That is, the roots are real and unequal, and the system is over damped. Next is, when zeta is between 0 and 1, the roots are minus zeta omega n plus or minus omega n into root of zeta square minus 1, and this is the zeta is between 0 and 1. So we can write this as 1 minus zeta square, because zeta is between 0 and 1, and here we get square root of minus 1, and that is minus plus or minus j. So square root of minus 1 is j here. So from here we take the square root of minus 1 outside. So that is equal to j. And this, that is omega n into square root of 1 minus theta square is omega d. So we get minus theta omega n plus or minus j omega d, where omega d is omega n into square root of 1 minus theta square. The unit is radian per second, where omega d is the damped frequency of oscillation of the system. Next is the response of undamped second order system for unit step input. So the standard form of the closed loop transfer function of the second order system is C of s divided by R of s equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. And for undamped system, zeta is equal to 0, and for unit step input R of s is R of s is equal to 1 by s. So C of s is equal to 1 by s into omega n square divided by, putting the theta equal to 0, we get s square plus omega n square. And after doing the partial fraction and after getting the inverse Laplace transform, we get C of t is equal to 1 minus cos omega n t. And this is the response of the undamped second order system for unit step input. Next is response of underdamped second order system with unit step input. So for underdamped system, the value of theta is between 0 and 1, and C of s equal to omega n square divided by s into s square plus 2 zeta omega ns plus omega n square. And after taking the Laplace transform, we get C of t is equal to 1 minus e raised to minus theta omega n t divided by root of 1 minus theta square into sine omega dt plus theta, where theta is tan inverse of root of 1 minus theta square divided by theta. And this is the response of the underdamped second order system with the unit step input. Next is response of second order system for critically damped and unit step input. So for critically damped system, the value of theta is equal to 1. So we get C of s equal to 1 by s omega n square divided by s plus omega n square. And after taking the Laplace transform, we get 1 minus e raised to minus omega nt into 1 plus omega nt. And this is the response of the second order system for critically damped and unit step input system. Next is response of second order system for overdamped and unit step input. So overdamped means the value of theta is greater than 1, and we get C of s divided by R of s equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. And putting s1 and s2 is equal to minus omega n into root of minus theta square minus 1 and theta omega n plus omega n into root of theta square minus 1 respectively, we get C of s equal to omega n square divided by s into s plus s1 into s plus s2. And after taking the Laplace transform, we get C of t is equal to inverse Laplace transform, we get C of t is equal to 1 minus omega n divided by 2 into root of theta square minus 1 into e raised to minus s1t divided by s1 minus e raised to minus s2t divided by s2, where s1 and s2 are these two values. And this is the response of the second order system for overdamped and unit step input system. So this is about the first order and second order system and their responses for unit step input. And thank you for watching the class. If you like the classes, please like, share and subscribe my channel.